the lecture for today. I guess uh, what I'll do is a very quick recap of where we were with the stiffness method, and then jump into this topic on inclined supports. How do you deal with inclined supports? There's one problem on your homework about that. And how do you deal with things like if a member is too short or too long? How do you deal with that? There's yet another problem on your homework for that too. So I'll jump straight away into uh, I'll jump straight away into uh, how we are actually solving this system of equations. So just to remind you, we were what the overall idea for this method was that given a truss structure, we'll divide it up into elements, find the force displacement relationship for each element uh, in its local coordinate system first, then transform it into its global coordinate system, and then simply add it or assemble it into this big system of equations. So we went through all of that last time, and we said that we can divide that system up into a free degrees of freedom, which where the displacements are unknown, and a specified degrees of freedom where the reactions are unknown. So once you divide the system up into these two parts, we said that you can sort of represent that system in these two block equations. And the way we solve it is to find the unknown displacement degrees of freedom first, uh, using the first equation of this matrix, and then find the unknown reaction forces from the second equation of that system. So I think that's about where we were last time. I had been showing you which parts of the code correspond to which sections of this stiffness method. So very quickly, what I'll do is remind you again that in this code, what we initially did was we set up these empty K, U, and F matrices. So maybe what I'll do is again place a breakpoint here. Let's see if I need a, well, hopefully not. Okay, so place a breakpoint here and click on the run button. Matlab asks me for the name of an input file, so I'll choose the first input file. And by the way, these codes are also up on Blackboard now, in case you haven't tried them yet. So from that input file, we get node information. There were 5 nodes in this problem. But just to remind you again, the problem that we are talking about is this one. This is an indeterminate problem. As you remember, we had solved with the flexibility method before. So we set up nodes. There are 5 nodes. There are 7 elements showing you which node is connected to which other node. There is the C matrix contains the Young's modulus for each element, area of cross section for each element, support locations. So 1, 3, and 5 nodes number 1, 3, and 5 have some supports and loads. The first thing we do is we construct these empty K, U, and F matrices and vectors. And then depending upon the boundary conditions, you have to determine which boundary conditions are, or which degrees of freedom are free and which are fixed. So I showed you last time that at the end of this loop, what we get is 3, 4, 6, 7, 8 are the free degrees of freedom, and 1, 2, 5, 9, 10 are the specified degrees of freedom for this particular truss. Similarly, then we add the nodal loads. So I'll skip to that. And now our force vector is computed correctly. And I was showing you last time that through this loop through lines 39 to 50, you loop through this and you build up this element stiffness matrix. And just as one example, maybe what I'll do is build it for one of the elements. I think last time we skipped element 3, so let me just show you for element 3. This is the first time the loop is running, so right now element is 1. I won't go through this. Go through element 2. and the third time it is going through is element number 3. So for element number 3, I'll go to this main subroutine that I showed you last time. So let's see what element 3 looks like. Element 3 is this element C, which is connected to nodes 2 and 3. So indeed it is inclined, which means that the 4x4 matrix that we get for this element would be all pretty much full, 4x4 non-zero elements. So let's see how that's constructed. I'll go into this subroutine by choosing step in. So if I go in, last time I also showed you how to construct these transformation matrix. Clearly, since this is a inclined element, so the transformation matrix of cosine, sine, minus sine, and cosine is non-zero. And the total element cosine, the transformation matrix, just as we saw in the notes, has a 2x2 transformation matrix here, a 2x2 same transformation matrix here, and 0 2x2 matrices on the off diagonals. So this transformation matrix is then used to convert this local element force displacement relationship. So for element 3, which is inclined, if you remember from what I just showed you, that inclined element has this particular matrix as the local force displacement relationship, right? The local force displacement relationship always looks like this: some non-zero number in rows and columns 1 and 3. Okay, because this is oriented along that slanting direction. We'll take this local force element displacement relationship, pre-multiply it with the transformation matrix, post-multiply it with transformation transpose, and that way we get the force displacement relationship in a global coordinate system. It is exactly the same relationship expressed in a different coordinate system. So obviously in a local coordinate system, the relationship is very simple. You get lots of zeros in there. But in the global coordinate system, if your element is oriented at some angle, in the global system, that relationship is not that simple. But it's not hard to calculate because Matlab obviously is able to do those matrix multiplications very easily. So once we have this, we send it back to the main program, and we find the elements that this or we find the nodes that this element is connected to. Clearly element 3, this element 3 is connected to nodes 2 and 3, which is degrees of freedom 3 and 4 at node 2 and 5 and 6 at node 3. So we find which degrees of freedom this element is connected to, and clearly it shows 5, 6, and 3, 4. Any idea why it's sort of in the reverse order, 5, 6, 3, 4? Because the connectivity, we said for element 3 is 3, 2, not 2, 3. So obviously element C or element 3, we can say that it's connected to 2, 3 or 2 and 3 or 3 and 2. It's the same thing. Okay, so in this case, the order does not matter. So that's why we have element degrees of freedom, which come out to be 5 and 6, which is for node 3, and 3 and 4, which is for node 2. And at this point, all we need to do is to go to the to the global stiffness matrix. So let me pull that up as well. The global stiffness matrix right now looks like this. There are only 2 elements added to this global stiffness matrix right now, element 1 and element 2. And you kind of roughly make out here where those 2 elements fit. When I add element 3, you will see that, just like I said, rows and columns 5 and 6 and rows and columns 3 and 4 will be affected. So let's do that. This one line is where that gets assembled. So go to the right rows and columns which correspond to the degrees of freedom and add the current k element matrix that we got from that subroutine. So that's what we're doing here. I executed that statement and go back to this guy, and you can see clearly that matrix was just added to this system. So in the same way, we can proceed with adding element 4. Oops. Okay, let me add, I think this is element 4. Element 5, let me remove that breakpoint so that we don't go into that again. Element 6, element 7, and at the end of element 7, we are done with the entire stiffness matrix, and this is the exact same stiffness matrix that you should have in your handout as well. So once we have this stiffness matrix, we said that to solve the system, we are going to use this solution procedure, so that the free degrees of freedom is equal to K free inverse times F free minus K free specified and times D specified. So I hope that you can see the analogy of that line in the handout with this line in Matlab. It's exactly one-to-one correspondence of that line in the of those two lines in the handout with these two lines in the Matlab code. So after I execute these two lines, I have the correct displacement at all the nodes. I have the correct forces at all the nodes of the structure, including any external reactions. Let me ask you this. If I were to go to Matlab command window and say F, so this is the current value of F, which is the forces acting on my truss, including external loads, including reactions and everything. If I do sum F, what should be the output? 0. Why? Because sum of forces in the X and the Y directions both have to be 0. And indeed, it is 0. Further, not only this, if I say sum of F1 colon 2 colon end, what does that mean? Anybody know what that means in Matlab? 1 colon 2 colon end. So I'm picking out certain elements from F. I'm picking out element 1. So when I say F of 1, I'm picking out element 1 of F. That's this guy. That's just the multiplier up there. Then I skip 2 and I pick out this one, and I skip 2 and I pick out this one, and skip 2 and pick out the next one until the end of this vector. So I'm picking out 1, 3, 5, 7, 9. What do those degrees of freedom correspond to? X direction. So the sum of forces better be 0 in the X direction by itself also, right? Let's check. Is it, so compared to 10 to the power 4, so you can see the forces are of the order of 10 to the power 4, but our answer is 0.1902, very close to 0. And the likely cause of this is that there is some rounding error in matrix inversion and those calculations. Let's check another thing. Sum of forces in the y direction. So I'll start with 2 this time. So I'm saying 2 colon 2 colon end. So sum of forces in the y direction better also be 0, 10 to the minus 13. I would have actually expected x direction also to be of that range, 10 to the minus 13. But I'll check why this is comparatively so large in comparison to 10 to the minus 13. So both sum of forces in the x and the y are 0. Okay. At this point, what we are doing here is actually checking for exactly that, which displacements and forces are close to 0. So I'll skip over that. And I'll go to this line number 69 in your handout. Let me see whether it's on the first page or the second page. I think on your handout, it's on the second page. Of now that I have all the correct displacements and all the correct forces for my truss, I should be able to calculate internal forces in the truss members, in each truss member. Unlike the force or flexibility method where we actually first calculated member forces and then calculated displacements. In the stiffness or displacement method, is the other way around. We first calculate displacements, and then we have to go back and calculate member forces. So let's see how we can calculate member forces. At this point, I'll first create a vector, an empty vector called element forces. Then I will go to each element, again using that for loop, go to each element, and let's see how we are calculating these element forces. I'll first check which nodes is this element 1 connected to. It's clearly connected to 1 and 2. I know the locations, the original undeformed locations. I know the degrees of freedom, 1, 2, and 3, 4. And then I'll again go back and call that truss subroutine. So I'll step in here, and once again I'll skip to that line because all of this we've already discussed. So at this point I have the K element for this for the element force displacement relationship for this element number 1. First question: are the local and the global element matrices different or the same for this element 1? And if you don't recall what element 1 was, maybe check your handouts. Element 1 is this element A, which is connected to nodes 1 and 2, oriented along the horizontal direction, where the local axis corresponds to the global axis. So indeed, that K local and this K global is exactly the same, because the transformation matrix is an identity matrix. Any matrix multiplied by with an identity matrix gives you back the same matrix. So we have the local force displacement relationships, and we also have the local displacement degrees of freedom. This U L doffs is telling me that at node 1 there is zero displacement in the X and the Y, as it should be, because that's a support, pin support. At node 2, I have some horizontal displacement and some vertical displacement. Okay. So using that information, I should be able to figure out how much did the element extend by, right? And in order to find how much did the element extend by, I'll calculate this U element. So for this U element, I'm doing T transpose times the degrees of freedom, or the display. So this U L doffs is what I got from the main code. So this is in global coordinate system. If I want to convert a vector which is in global coordinate system to something that is in local coordinate system, you remember we said we are going to multiply that with T transpose. And if you don't remember where in the handout that is, it should be on the 3rd page right here. I have some displacement vector at node 2. I know its values in the global coordinate system, X and Y. Those are the ones that we solved in the main program. I want to convert them into the local coordinate system. So to go from a global coordinate system to a local coordinate system, I use T transpose. Right? Pre-multiply by T transpose, and I will get the local displacements for both those nodes. And clearly we see that the local displacements in the X prime, Y prime system are 0, 0 at 1, because of course 1 doesn't move, and some small number in X prime and some number in Y prime. Okay. Now let me ask you this: what is the change in length of the element if we know that this number is X prime, this number is Y prime? What is the change in length of the element? Say again. In X prime. So you remember we talked about this when we were looking at this picture. We said that where's my element? Here. So if I'm looking at a particular element in some orientation, then the change in length of the element is governed only by the X prime components. If I have some displacement in the Y prime components, that does not, small displacement in the Y prime components, that does not cause change in length of the element. Okay. So using that information, I can immediately calculate the forces at the two ends, because now I have the local force displacement, I have the local displacements of this element. So if I go here, that's what we do next. When I execute this line, I take the K local matrix times the U displacements in the local coordinate system, and to get local forces. Clearly, it has forces minus Fm and plus Fm in the 1 and 3 components, as it should, right? Because what we are talking about is computing this guy. Since we know the local displacements, we take multiply it by the local stiffness matrix to get something in the 1 and 3 components, which actually is the internal member force, right? This minus Fm and Fm, that's the internal force in this element. So so now I know the internal force in this element, and we can go and plot it in the main, or we can just record it in our element forces vector. So we keep doing that same thing for all of those elements, and at the end of this for loop, which I'll just run through here, at the end of this, I have 7 element forces recorded here, and it so happens that 2 of those elements are zero force elements. Okay. And the rest of it is just plotting and checking. So I'll execute that, and Matlab plots the deformed shape of the truss. You can zoom into any location and see whether those reactions make sense. Clearly, there is no displacement here. It gives you the reaction values. It also gives you the element forces. It shows you the deformed shape, and you can also verify that at the location of the roller, for this particular problem, there is no displacement at the x direction. Also, it just so happens like that. But I can run a different problem, and at this point, actually, the code is done. So I'll execute that, run it with yet another input file. So once again, this is a different truss problem. This is example 2 in the codes that I posted on Matlab or on Blackboard. This is a Warren truss with 1, 2, 3, 4, 5, 6, 7 elements again, and 5 nodes, and a center load of 10,000 units. And a quick word about units, if I haven't already mentioned, Matlab has no way of knowing what units you are using. Any computer program does not have any way of knowing what units you are using. You have to make sure that your input file is self-consistent in terms of units. Matlab just knows that this is 10,000 units of load. Okay, it doesn't know whether it's kilonewtons or pounds or kips or what. So you have to write your input file in a way that is self-consistent in terms of units. The thing that I wanted to quickly show you here was that this was a roller, this was a pin support, there's a load here, and if we look at the roller support, clearly it has some displacement in the x direction, but no displacement in the y direction. So there are other input files in the folder that I posted on Blackboard. Make sure you go through them, take a look at exactly how Matlab is computing everything for those files, and then I'll do some more examples here as well. In particular, there is one example in your handout, which is this one. I think this one is input file number 3 in the on the folder. So this is 3 element truss. First question, is it determinate or indeterminate? Indeterminate. And to what degree? To degree. So how many say 3? How many say 2? How many say 1? It's to degree 1, because if you cut any of those elements, it becomes a determinate truss, right? So yeah, you don't always have to add up equations and unknowns to check the degree of indeterminacy. You cut any one of those elements and it will become a determinate truss. And clearly there are no loads on this truss. But the question simply says that node 1, which is this guy, node 1 settles down by 25 millimeters and find the force in element 2, and actually the code will find the forces in all the elements anyway, so it doesn't really matter. AE values are given to us. So let's see how to solve this. And we'll do this again by going through the Matlab code one line at a time. And the most interesting line, of course, is, or the most interesting place is this for loop where we create that element stiffness matrix. So let me run this. Matlab asks me for the file name. I'll choose 3. And then we are already at this point. We have the force vector already built. There's no forces, so clearly everything is 0. We have the u, or the displacement vector, also built. Displacement vector with all the specified degrees of freedom are already in there. There is clearly something non-zero at the second component. Why is there? Why is there a non-zero second component? Mongzi? Let's read the problem again. Support node, node 1 settles down by 25 millimeters. So the degrees of freedom corresponding to node 1 are, what are the degrees of freedom for node 1? 1 and 2, which means that the y direction will have degree of freedom 2, where the displacement is known to be minus 25 millimeters. So in the input file, maybe I should show the input file also here. The input file is just those 5 or 4 nodes in this case, 3 elements with their Young's modulus and area of cross section. Boundary conditions, there are 6 total number of boundary conditions here. 2 at node 1, 2 at node 3, 2 at node 4, and at node 1 it is saying that the second degree of freedom has a displacement of minus 0.025. So that's just the input file. There's no loads, so that part is empty. And that's why in the Matlab code we can see that degree of freedom 2 already has the specified displacement in there. We'll go through this loop to build the K stiffness matrix now. First question, what would be the size of the global stiffness matrix? Jenna? There are 4 nodes. So 2 degrees of freedom at each node, and that would be 8 cross 8, right? So what we have now is an empty, completely empty 8 cross 8. So what we'll do is we try to fill that in. Let me ask you this. Element 1 is in the vertical direction. So should the local force displacement relationship be the same as the global force displacement relationship? It won't, right? No, because the local force displacement relationship is oriented along the x prime, y prime direction, and the x prime, y prime direction coincides with x global xy only in this horizontal configuration. If I have an element in the vertical configuration, the x prime, y prime is oriented like that, which is different. So which is different from the global coordinate system, and we'll easily verify this. So we'll step in here, we'll compute the local element stiffness matrix, which has non-zero elements in the 1 and 3 rows and columns. 1 and 3 degrees of freedom correspond to x prime, y prime directions. right? And as soon as I do the transformation, as soon as I do the transformation from this vertical local coordinate system to the global coordinate system, we get something that is that has non-zero, exactly the same non-zero entries in columns 2 and 4, because columns 2 and 4 really are corresponding to the global y direction. So we can check that easily. Any element that is vertical. So I think if you remember last time, element 2 was vertical. And maybe even before that, for this element 2, the local degrees of freedom along the let me go to this one. Um, yeah, so for a vertical element, the local y prime would be along global minus x. So that's why this k element matrix, uh, this is element stiffness matrix in the global coordinate system, has non-zero entries in those non-zero entries get shifted just by one row and column. So that's for element 1. Keep going and go to element 2. Element 2 in our current problem is this inclined element. So once again, we'll go into that subroutine, calculate the local stiffness matrix. Local stiffness matrix structure is always like this. The transformation matrix is non-zero or non-identity, where we clearly see those sub 2 cross 2 transformations of local coordinate system to global coordinate system. That causes the global element stiffness matrix to be all full non-zeros in the 4 cross 4. That gets assembled to the global K. Um, and maybe just before I do that, so this is the assembly step. Just before I assemble it, let's take a look at what that matrix looks like. So we'll go to the K editor. It's a 8 cross 8, mostly zeros with these entries that were added to it from element 1. I'll add element 2, and let me ask you this: what rows and columns would change? For element 2, element 2 is connected to nodes 2 and 3. So what rows and columns would change? The degrees of freedom corresponding to nodes 2 and 3, which would be 3, 4, and 5, 6, right? And we can check that in our Matlab code as well. Sorry, where is this one? Element degrees of freedom are 5, 6, 3, 4, right? So once I add this guy, we can go back to Matlab and check indeed those 3, 4, and 5, 6 degrees of freedom were changed. The same process is repeated for element 3. And at the end of this loop, we have the correct K matrix built. We already have partial U, where every specified degrees of freedom is known. We execute that statement again, and just in one line, I know now what are the actual displacements of that entire truss. Still, most of it looks zero. Why is that? Right, because the truss really has 3 supports and only 2 degrees of freedom corresponding to node 2 are free. In addition, there should be some displacement at degree of freedom 2 for node 1, which is what the problem states. So there should be 3 total non-zero displacements. And indeed, that's what we get. We get x and y for node 1, x and y for node 2, and x and y for node 3 and 4 are zeros. And this next line calculates the support reactions. Um, and those support reactions are also exactly the other degrees of freedom. The degrees of freedom that are specified, those have the ones that have some reaction force. The free degrees of freedom don't have any reaction or any external force for this particular problem, right? And you can check the sum of forces in the same way that I showed you for the previous problem. And at this point, what we'll do is we'll go to computation of those element forces. So for the element forces, once again, we'll go through the for loop, go in here and inside here, go to this line. These last 3 or 4 lines in that truss element 2D is what calculates the internal element forces. This one line 27 takes the local or takes the global degrees of freedom, which for element 1, which is connecting nodes 1 and 2, this 4 cross 1 represents the global displacements. And this is the transformation matrix that gets converted to local displacements, and using those local displacements and times the force element relationship in the local coordinates, we can calculate forces. And local forces will always have this structure, minus Fm plus Fm, right? That Fm is the internal force in that member. So member 1 seems to be in tension or compression. Let me ask you that first. From this, F1 is minus 8.33 and F3 is 8.33. So is that tension or compression? Tension, right? That's exactly what we also had in our handout. So I'll keep going through that. Let me remove that breakpoint. And this plots the final configuration of the truss as well. So if you zoom into node 3, you can see that initially the node was here and it dropped down to this location. That's the 25 millimeters settlement of that node, and which caused tension in this member, in the vertical member, compression in the diagonal member, minus 13,889, and tension also in the top member. Okay. Here's an aside question. If I have this truss structure was indeterminate, right? We said indeterminate to degree 1. And if the truss structure is, if you have a determinate truss, no loads, and one of the supports settles, then what would be the internal forces in the members? So if any of the, let's say I do have a determinate truss problem, so I'll run that. The problem 2 that I just showed you, here there was a load, and instead of the load, if there is 0 load, and if I have a vertical settlement of one of the supports, what would the internal forces in the truss be? 0, because the truss would just rotate as a rigid body, right? It's only because the truss structure that we just, in the example that we did, that was an indeterminate truss structure. That's why it caused internal forces in the other members. If it's a determinate truss, support settlement or some member getting extended or shortened does not cause any change. Okay. So looks like we are still short of time here, but let me move on to this topic of inclined supports, which will be helpful for your problem 3, I believe, on homework 8. So as you often have come across, in there are problems where some supports are at an angle. For example, here this support 2 is at an angle of 45 degrees. Here you cannot say that one of the specifically whether x or y direction is fixed. If it was a vertical if it was a horizontal roller, then you would say y direction displacement is 0. But what you want to say here is that you want to create a new coordinate system, which is x double prime, y double prime, okay? And the degrees of freedom corresponding to that, as I've marked, are 3 double prime, 4 double prime. So what we want to do is to convert the global, uh, uh, we want to convert the global coordinate system at that particular node into an inclined coordinate system. And as a word of caution also, if you look at your book, the way that they deal with inclined supports is just completely unnecessarily too complicated. Um, what they suggest is to go to actually each element, rotate their element stiffness matrices, and then assemble them. There's no need to do that. You can just assemble the global stiffness matrix and simply transform the global degrees of freedom rather than the local degrees of freedom. Um, so let's see how to do that. The idea here is exactly to follow what we did for normal horizontal or vertical supports. So we know how to solve systems with horizontal or vertical supports. At the end of the day, we should end up with some stiffness matrix that looks like this. Okay. Now the problem with this is that for this particular system, there are 6 degrees of freedom. So you would have a 6 cross 6 global stiffness matrix. You have 6 degrees of freedom, of which degrees of freedom 1 and 2 are free. Um, 3 and 4 both have a mix of free and specified, and 5 and 6 are specified, right? So I know that these two are 0. I don't know these two, but I know that some combination of 3 4, one of those degrees of some combination of degrees of freedom 3 and 4 uh, is partially specified and partially free. So to actually separate out that degree of freedom, what we're going to do is to convert the degrees of freedom 3 and 4 from from this global system to an alternative 3 double prime, 4 double prime system, which is oriented along that support. So any ideas of how we can convert degrees of freedom 3 and 4 to 3 prime and 4 prime? Right, we'll use that cosine and sine transformation matrix. And if you remember which one, whether it should be transformation matrix this transformation matrix, or should it be T transpose? T transpose, right? We need to go from global to some alternative. So we need to have T transpose here, cosine, sine, minus sine, cosine. I'll write that out here. Um, so I need to have cosine, sine, minus sine, and cosine, and that happens to be T transpose. So what we'll do is, in order to convert only the 3 and 4 degrees of freedom, in order to convert the displacements only in those degrees of freedom, what we'll do is we'll pre-multiply it with a matrix that looks primarily like an identity matrix, right? So this is a 6 cross 6 identity matrix. The way I've written, it's an identity matrix multiplying a 6 cross 1 vector, which does not change anything, right? Identity matrix times a vector gives you back the same vector. What we want is to pick out the 3 and 4 components of that matrix and replace that with this transformation matrix. So I'll write that as cosine, sine, minus sine, and cosine. And in doing that, what I've done is pre-multiplied it with T transpose. But the problem is that I cannot just go in and multiply that equation that I had, that was an equilibrium equation. I cannot change that equilibrium equation as I please. to make sure that I don't change the overall equation, I will also pre-multiply it with another um, um, transformation matrix, which is the transpose of that. So that would be C minus S, S, and C. And the other entries are 1 and 1. And that matrix is the transformation matrix. So let me ask you this. What is T times T transpose for this particular matrix? T and T transpose. You remember this is an orthogonal matrix, right? So T transpose is actually equal to T inverse. So T times T inverse is just an identity matrix, right? It's an identity matrix, which means that by doing this operation, I have not changed the global system. And that's the most important thing. That global system or this global system represents equilibrium. I cannot change that willy-nilly. But I can change the degrees of freedom by doing some transformations internally within that equation. So by pre-multiplying this guy with T transpose and pre-multiplying that entire thing by T, I have not changed the global equation, but I have changed the local degrees of freedom. And very quickly, what that amounts to doing is taking that global system of equations and kind of inserting this T times T transpose right here. So if I insert T times T transpose, which is an identity matrix, if I insert that identity matrix between this matrix and vector multiply, that doesn't change anything, right? That doesn't change the global equilibrium equation. And in addition to that, what we'll also do is we'll take the entire equation and we will pre-multiply that by T transpose. That's the transformation required to take the global coordinate system at degrees of freedom 3 and 4 to rotate it to 3 double prime, 4 double prime only at that node. Everything else, all the other degrees of freedom remain exactly the same. Okay, so just to make that a little more concrete, this guy now becomes D double prime, which looks like D1, D2 in the global coordinate system, D5, D6 also in the global coordinate system, but D3 double prime and D4 double prime in the inclined coordinate system. So using this, we can then express that matrix as a modified stiffness matrix, that global vector, and just to be consistent with that, I'll call this DG prime as well. So this is DG prime, that DG prime, and on the right hand side I have T transpose times F, which becomes FG prime, and we get a slightly modified system of equations which we solve exactly the same way by splitting it up into free and specified degrees of freedom. Okay, so that should give you some idea of how to treat systems with inclined supports. What I'll also do is I'll post a modified main file for the Matlab codes that will help you kind of fill in the blanks of how to do this. Okay. All right. So I'll see you back on Friday. I still need to cover how to deal with length changes and effect of temperature and all that. So maybe what I'll do is I'll give you some more detailed hints about how to do that. That will help you solve problem 4 on homework 8. All right. See you all on Friday.